Hello, everyone. First of all, I would like to thank Protochips for organizing this flash talk. My name is Carolin, and today I would like to talk to you about our work on studying the surfaces of iridium oxide catalysts for water oxidation that was published in Nature Catalysis last year. So, water oxidation, or water splitting, is a process that's critical to the green energy transition as it produces hydrogen from non-fossil energy carriers that can then itself be used as a fuel. So, that is done through a process called water electrolysis using one of several configurations. In this diagram right here, I'm showing the proton exchange membrane water electrolyzer, which at the anode side of it takes in water, and oxygen and protons come out. And those protons travel across this membrane to the cathode side where they get reduced into gaseous hydrogen. And so as you can see from the setup, both sides, the cathode and the anode, require really expensive noble metal catalysts. Cathode catalysts are typically platinum-based, while anode catalysts are iridium oxide. And iridium is one of the rarest elements on Earth, and it's the key driver for water electrolyzer cost. And so in order to achieve widespread commercial use of this technology, we need to maximize catalyst activity, maximize its durability, and also minimize the noble metal content to drive the cost down. So I'll talk a bit about these anode reactions and the iridium oxide materials that are used to split water into oxygen and protons. So what we know about iridium oxides. The base iridium oxide forms a rutile structure, just like titanium oxide does. It is quite stable to the extreme oxidative environments in a water electrolyzer. It's not all that active. And so over time, there have been many variants of iridium oxides developed to increase activity and durability. One of the class of materials that's been studied quite a bit are these iridate perovskites, such as the strontium iridate, for example, because these tend to be more active for oxygen evolution. But at the same time, they reduce the amount of iridium that's present in the catalyst. And so there's been a number of studies on these iridate perovskites. But what's interesting about them is that we don't know fully why they are as good as water splitting as they are. And so when we look at this strontium iridate perovskite, the pristine material is fully crystalline. It has a clean crystal surface. And then as it is used in the electrolyzer in the acidic environments and oxidative conditions, the strontium starts to leach out and results in this reduced crystallinity surface here. And you can see over time that this like amorphous surface forms on the catalyst. And it maintains that kind of morphology. What's interesting, though, is that initially, as this catalyst is used and this surface becomes amorphous, the activity actually increases and it performs better. And then over time, the activity drops until it eventually dies. However, structurally, there is no super obvious difference between this really highly active catalyst with an amorphous surface and the dead catalyst with an amorphous surface. And so we were wondering how can we figure out like what is it about the surface? Clearly, it looks the same, but it isn't. That makes this catalyst first perform better and then worse. And the key question there is one of characterization. How do we study an amorphous surface on top of a bulk crystal? Most characterization techniques out there are just going to give a signal from the bulk crystal, and it's going to be pretty much impossible to get anything from this really low crystallinity surface. And so our approach to that was to try and see if we can take this surface layer of the bulk perovskite, roughly 5 nanometers in depth, and we turn this bulk system into a nanoparticle system. If we make roughly 10 nanometer size nanoparticles out of it, one would expect those to exclusively be surface, basically. So they should be this amorphous-like structure without having a bulk crystal inside of them, and that should enable us to study them better. And so we were able to synthesize materials like this, starting from the base iridium oxide. It turns out if you use your standard equivalent of strontium, And on calcination, you form the perovskite strontium iridate that we've seen before. If you use a large excess of strontium, that intercalates and goes into all those iridium nanoparticles. And when you then wash that out with acid, you are left with this iridium oxide structure that has no bulk crystallinity to it. You can see that in the powder XRD pattern that is almost featureless. And when you look at it in the TEM, you can see the nanoparticle region here that is not crystalline. It's also not amorphous. It looks almost glassy. And so that's a really interesting material to study. And so we then went ahead and took a look at what can we learn about the structural motifs that are present in this nanoscale catalyst material, and how we can go and compare that to the perovskite. So looking at the structural motifs that are present in the pristine catalyst materials, that like the as-synthesized catalysts, we first see again this almost amorphous looking structure. There's a little bit of a feature in the FFT here. And our first method of taking a look at these was using the X-ray pair distribution function, XPDF, that we can calculate from X-ray scattering experiments. And so we have from the bottom to the top here, this is just the rutile iridium oxide. And you can see this is a bulk crystal, so you can see crystalline features all the way in the really far radial distances. And the same is true for the strontium iridate perovskite. Both of these are bulk crystals. And then when you look at our almost paracrystalline iridium oxide, you see it has short range order, right? We have very specific motifs that are present in the up to like 9 angstroms of distance. And after that, you have no more order that's present in this material. And so from the different kind of motifs that we find in these patterns, together with like X-ray absorption and XFS data, we can deduce what kind of structural motifs are present in these materials. So in an iridium oxide, the base motif is always this iridium-06 octahedral unit. And we find different kinds of bond distances present. We find the iridium-iridium distance for edge-sharing octahedra at 3.1 angstroms. And we find the iridium-iridium distance for corner-sharing octahedra at 3.6 angstroms. And so we have 3 types of structural motifs that are present. This type 1, that is just the set of edge-sharing octahedral units that repeat across. The type 2 connections that are present in the rutile structures, which are a combination of edge and corner-sharing octahedra. And then the type 3 connections that are corner-sharing octahedra only. And so now that we have a really good idea about what these pristine catalyst materials look like, we then need to go and figure out, okay, now that if we use those catalysts and we subject them to whatever transformations occur when they do water splitting, how do they transform? And how does then our iridium oxide match with that amorphous surface that forms on the strontium iridate? Before we get to do that, though, turns out we run into an even bigger problem than that, which is that these paracrystalline oxide are exceedingly sensitive and reduce pretty much immediately under the electron beam, which is not entirely surprising. A noble metal oxide, when you shoot electrons at it, is going to reduce out, and that's exactly what happens here. So you can see over here, this square region, this is where an EDS map was collected, and you see the massive change in structure as you zoom out from there. And when you look at it, you can see all these tiny crystallites that have formed all over this area. And even on the perovskite surface, on the left here, you see basically the first frame that was captured in this area, and you can see this surface layer that looks pretty much amorphous. And already on the second frame, you start to see the changes and the first kind of aggregations and lattice fringes that start to show up here. And so this is where I started using the protochip system basically just as a frame grabber, because it lets me run around those catalyst materials and make sure I get to capture the very first frame at each region I look at. And then going on from there, I can, of course, stay on an area for a while and make sure that I can visualize the transformation that happens. So if you look to the right, you can see how under exposure, this material immediately starts shrinking and crystallizing out, and you can see in the Fourier transform how the crystal lattice forms. And I'll let this play for a bit, but you can see how quickly the initial transformation happens. Immediately on the first frame, you see how this starts to shrink, and then the crystallites form. This entire amorphous part becomes less and less and grows over on the surface over here. And if you watch up here, you see the large crystal aggregates that start to form over here. And so you can see, if you look to the right over here, you see this kind of blurred region at the edge of the frame. That's the axon drift correction, making sure this frame stays in place, because you can see this is drifting actually quite a bit. And you can see none of that in the final video because it corrects this out, even though the entire material transforms as it's moving. And so this is, even though we're not doing in situ experiments per se, this lets us work with these exceedingly sensitive materials and lets us capture the precise dynamics that go on in a material like this. And this turns out to be really critical because there's a lot of conflicting opinions in literature as to what happens to these materials, how they form. Some reports show that there are crystallites on the surface. Some claim the surface is completely amorphous. And none of them have a good discussion on beam damage. And so if you're not really, really careful when you look at materials like this, you can miss details like this, which by capturing every single frame and putting it together like this, we're able to visualize in a way that wouldn't be possible otherwise. So now that we have a way that lets us look at these materials and make sure we capture the phenomena that we want to see, let's compare the iridium oxide to our perovskite surface. And so as we use these catalysts in electrochemical systems, one thing to note is that we can't use the X-ray pair distribution function anymore because in order to use them as catalysts, we mix them with carbon black, we put them on carbon paper, and all the X-rays that we would see coming out afterward, all the signal would be from the carbon. And so what we do instead is we use the electronic equivalent of it using the electron pair distribution functions coming out of our electron microscope. And so over here, this panel is our iridium oxide material, and then the other three are different regions of the perovskite after it's been used for catalysis. And then we get the pair distributions out from the local amorphous diffraction patterns. And we can map that in the same way we saw earlier for the X-ray pair distribution function, which we show up here for comparison. And so we find that, again, in our iridium oxide, we have the set of these three types of octahedral connections. And these are also present in some of the regions that we see in the perovskite, like over here. This matches the same type of three different orientations. There are also regions in the perovskite that show only the type 1 phase sharing octahedra, as well as there are regions that only show corner sharing octahedra. So the structure in the perovskite surface is a little bit more heterogeneous than what we've seen in our base iridium oxide material, but still the same kind of structural motifs are present in both surfaces, which means we get to use our paracrystalline iridium oxide as a proxy for this perovskite surface. Now, let's take a look at how those structural motifs dictate the activity of our material. Now, just as a summary, we have our iridium oxide that has homogeneous short-range order and these three types of iridium-06 octahedral units, versus we have the surface of our perovskite, which also has short-range order on the same length scale. And some areas show these three types of connections, versus there are others that show type 1 or type 3 only. For comparison, we also have the bulk strontium iridate perovskite, which has long-range order and shows these perovskite type corner sharing octahedra. And our base iridium oxide, which is the rutile structure and shows the long-range order type 2 only. Now, on the plot on the right, you can see the current densities, i.e. activities of our different catalysts, pristine ones, and then after certain times of using them, compared to the pristine iridium oxide. And you can see that the type 1 connections actually stay relatively constant as this catalyst is used. So we don't lose type 1 connectivity as this catalyst is cycled. That is a different story for the type 2 or 3 connections, where in the pristine iridium oxide, that type 2 stays the same. It has no other way of connecting. But our iridium oxide, you can see that connectivity drop over time as that catalyst is used. So it seems that these type 2 or 3 connections seem to kind of be less stable and break apart as that catalyst is used, and that contributes to both its activity and how it degrades. So having learned all of those parts, we can now summarize the structural evolution of our iridium oxide. So we have the initial state of our material here that is characterized by a mixture of type 1 and type 2 and 3, edge sharing and corner sharing octahedra. And the arrows here point to the active sites as calculated by DFT. And so initially, all those octahedra are really tightly interconnected. And we have this kind of lower activity type 1 active site and a fairly low iridium oxidation state. And then as the activity of that catalyst increases and that surface becomes amorphous on the perovskite site, what happens is that, as we saw, the type 1 connections stay the way that they are, but we start to lose some of the type 2 connectivity, which produces more type 3 connectivity. Makes sense. You break edge sharing octahedron into corner sharing ones first, and that creates more iridium vacancies. What it does do, though, is as this starts to break apart, is you generate more active sites, which is why the catalyst activity increases initially, even though some of the structural features start to change. And then over time, that same change continues and until you reach a point where there's too much breakage of the type 2 and 3 corner sharing octahedra, which then leaves individual species that can leach away or become electrically detached from the base electrode. And so that is how the same kind of structural transformation and degradation first increases and then decreases activity until this catalyst dies. And so this is highly significant, not just for the iridium oxides, because knowing what the structural motifs are that dictate the activity for water splitting means that we can use that to design the next generation of catalysts that will feature those specific design motifs. And that'll let us make much more active and much more stable catalysts for water oxidation without needing this really high iridium loading. And hopefully that'll let us make a dent in the challenges that prevent PEM water electrolysis from being commercially viable at a large scale at the moment. So with that, I would, of course, like to acknowledge all the other authors that were part of this study across several groups at Northwestern University. And I would like to thank everybody who was part of this project and the journey in making this work happen. And I would like to thank all of you for listening. And with that, thank you very much.